So next on the list, we are going to talk about computing volumes in solids. And my 4 techniques are going to be by slicing, by disk, by washer, although disk and washer to me, they're really the same. And then by cylindrical shell method. So let me start off with a couple examples of computing a volume of a solid in 3 space by looking at cross-sectional slices. Now on the board, I admit, I don't have the 3-dimensional solid drawn, and I'm not going to draw it. However, let me describe it for you. Let's just imagine I got a solid in 3 space, whose base is the region bounded by the graph of that line in this particular parabola. Sorry, that should be 1 unit up, shouldn't it? And suppose that any cross-sectional slice that is perpendicular to both the base and the y-axis are going to be semicircles whose diameters are on the base. So you can imagine basically the solid has this as a base, but all these cross-sectional slices are nothing more than semicircles with the diameter on the base. Now, I'm trying not to get into a lot of theory with these videos because they have to be so condensed, but just very, very quickly, if you take a peek at the base of a cross-sectional slice, let me change colors to blue. My red wasn't showing up very well. Notice how the length of that side right there is just a small change in the y direction. And so theoretically, here's how you want to compute the volume. We're going to say the volume. It's going to be nothing more than the volume of one of these individual slices. Semicircle coming off the board. Plant your feet on the y-axis, look straight down, and you're going to see some 2-dimensional surface. We're going to compute the area of the surface and multiply it by thickness, which is a small change in y. I refer to as delta y. Now, you know what we're going to do this in the end. We're going to take the limit of the Riemann sum, convert it to a definite integral. And so it certainly will have to be the case that this is an area function in the variable y, since that's going to naturally transform into a dy when I rewrite the limit of the Riemann sum as a definite integral. And so if I take a peek at the sum, as y ranges from 1 to n, and we'll look at an arbitrary y value each of those subintervals, and I'll take the limit of this as n increases without bound. And this is going to give me a definite integral from a to b of some area function in y, and we'll be integrating respect to y. That's how I'm going to compute the volume of the solid. Now, of course, if my cross-sectional slices were perpendicular to the x-axis, this would be an area function in x. This will be a bx. So let me dive in. In setting up an integral, to compute the volume. So take a peek at how this diameter ranges from one curve to another, but then changes those curves once I get to this point of intersection between this line and this parabola. So I think for now, my values for y are simply going to range from 1 to positive 2, because 2 is the y coordinate at that point of intersection. So I'll integrate from 1 to 2. I do think the area that facade, the face, when I'm standing way up high on the y-axis, looking down towards the x-axis, is a semicircle. And a semicircle's area is computed by looking at pi halves times the radius squared. And we're integrating with respect to y. Now, as far as the radius is concerned, notice how this curve right here, the right-hand portion of the parabola, can be describing a function for x in terms of y, namely this one. Whereas this curve over here, that is to say, the portion of that parabola in the left-hand plane, describing x as a function of y for that curve, I see that x is this. So it looks to me like the diameter of the semicircle is this large x value here minus a small x value here. Well, here's a large one. Here's a small one. And if I subtract them, then that'll give me the diameter of the semicircle. So I'll cut that in half. This will be the radius, and that is what's being squared. And we're integrating with respect to the variable y. However, this is only going to give me the portion of the volume for y values ranging from 1 to 2. Now range from 2 to 5, I'll add another interval. I'm still integrating with respect to y. But let's take a break and talk about the diameter of such a semicircle. It'll still really be a large x value minus a small one. But I don't have an algebraic description of the line, so let me take a break. Let me consider my MathD point slope formula for the equation of a line. So I do believe the diameter of such a semicircle where that's the base portion of it. And I believe the diameter can be described by this large x value here, minus the small x value here described in terms of y. But that's the diameter. So here's the radius. I'll square that radius. Now I'll integrate with respect to y. So if you don't mind, I'll leave the rest for you. I'll concentrate on setting up examples. By the way, everybody, before you leave, notice the scoring looks a little off. Looks better.